we go into it, I'm going to give you some tools that are going to, some tools that will help to understand sort of the same language we're going to speak. So, are you the only engineer in this room? Anyone else? Engineering, physics? You got another one?
Little physics.
Remind me your name again? Marissa. Oh, that's right, yeah. You look different without the helmet.
Hopefully.
Alright, so the first thing we're going to talk about is the idea of vector. And what a vector means is that you have something like, we say, here we are in Boulder, and we want to go how far to New York, right? And you're like 2,000 miles, and you're like, okay, this way? No. You have to have it both a distance and a direction. And we represent our distance with how long our arrow is, and the direction, obviously, where it's pointing. And it doesn't have to be a distance, it could be a weight, force, speed. All the idea is we have just a magnitude and a direction. And talk about how those things add together. So let's say here's a riverbank, and stream is going down like this. Say it's going at 5 miles an hour. So we're going to represent that as a 5 mile an hour arrow. And let's say you want to swim across, and you can only swim at 2 miles an hour. Be like this. So if you want to talk about how would you represent your speed relative to the shore bank, what you would do is you would add those two together by just putting the nose and tail together. And then you take the straight line distance. So this guy here is your actual vector sum. And you can do your geometry, your Pythagorean theorem and stuff, which is not important for today. That's just the general idea. You can see that you add those together, you get something that's a little bit longer. And it's going to be inclined, it's going to be somewhere between the direction of those two. And of course, if I add the arrows like this, they add together, if I add them like this, the net result is this guy right here, and so on and so forth. So we're going to need that, because we're going to talk about a very boring, I guess, oh yeah, recording, great.
Yep.
So we're going to talk about a very boring wing. It's very square and interesting. And it's going to be sitting here in space doing nothing, except that it has some weight, which I'm going to call weight here. And it's sitting here in air, and you've got a force of gravity acting on it. It's going to start falling, right? And it's going to keep falling, and as it starts falling, it's going to run into all these little air molecules, and those are going to add a drag. It's going to slow it down, so it's going to fall. It's going to keep falling, but it's going to be accelerating less and less until this grows and grows and grows until those two forces balance each other out. Now it's falling at terminal velocity. That's not very interesting. So what would happen if instead that wing, that glider was tilted? Now, it's still going to have weight, gravity's still going to be falling on it, and as it hits those air molecules, what's going to happen is they're going to have nowhere to go but get deflected. So you're going to get, the airstream's going to come like this, and it's going to have to run along the side, and it's going to do something like this. So that resistance, that drag, is now going to be doing this kind of thing. And because the air is flowing along the glider like this, it's also going to be rubbing and having friction. So it's going to add something like this. So we're going to have our weight, we're going to have our lift, and we're going to have our drag. And if we, just off to the side, add those together. So I'm going to take this weight arrow, I'm going to take our lift arrow, and our drag arrow, and our net result is nothing. Nothing happens. So this is a stable system. It's just going to sit here doing its thing. And as far as relative to the air is concerned, our wing is traveling like this. Mark's not working very well. All right. So I'm going to erase the wind lines now, just so we can make everything a little more clear. have our very boring airfoil with weight. That lift is going to act perpendicular to the glider and our drag. And it's going to be moving along this path. And, the air that's coming into it is going to be coming up from an angle like this. It's going to be falling through the air, or falling through the sky, air gets deflected. And you can see that we draw an imaginary line that's right down the middle for airfoil. We get this guy. I'm going to name this. So we'll call this guy the relative wind or flight path. Call this the sort of the fuselaging, where the fuselage is oriented. If we're referencing to the ground here, call this the pitch angle. Pitch being our up-down reference. We also have yaw, which is our left-right, and our roll, which is side-to-side. This angle between how the wing is oriented and the wind is our angle of attack. And yeah, we'll start with that for now. So we can do better in this square little wing because whenever air flows around something, it doesn't really like sharp angles. It hits like a box like this and it goes around, ends up trying to curve around, and it makes all these little turbulent eddies around everything. So that's why we make stuff nice and round and streamlined. And especially when air flows off the backside of something, it really doesn't like to have a big gap here. That's why like cars and anytime if you ever look at the cross section of the wing, it tapers down. So we're trying to help that air come back together in a nice controlled way, so it doesn't make this like vacuum here. Because you can think about this object plowing through all these air molecules. They're sitting here and push them out of the way. There's nothing behind it. So they try to suck back in, and it creates a lot of turbulence and drag. So that's why we taper it off. Taper off the backside and round the front side, so you get this nice little teardrop airfoil shape. That's where it comes from. There's nothing magical or special about that shape. It just is a good way to balance out lift and drag, balance out our drag and minimize it. And the lift actually comes from how the air is impacting that airfoil. So we're going to go away from our square airfoil, and we're going to zoom in on our little teardrop here. This part is really dying. Okay. So we have our airfoil, and it produces lift, and drag affects it, and it has its weight, and these all bounce out.
Really quick, Chris, are we looking at this from the side?
Yeah, sorry. So yeah, we're looking like, if we're looking at our plane, the plane's flying this way, you're cut a cross section, we're just looking at it side on.
Okay.
And our wind is approaching like this. I wonder if we have dry erase markers. We did not expect this one to die on me so badly. Okay. And this line here, call our chord line. This angle here, angle back again. So the actual amount of lift that this guy produces, lift, is going to be proportional, sort of a fake equals sign here. So it's not an exact formula, but the idea is you have our called coefficient of lift, which has to do with sort of overall geometry of whatever object we're using. If it's a flat plate, if it's a ball, if it's an airfoil, it'll be some number that can be experimentally derived and measured. It's not particularly important other than knowing that there's just this black box depending on what shape you're using. It's going to depend on the density of what you're going through. So this would work in air or water or honey or any sort of fluid. that's going through will have some density, and it'll be proportional to our angle of attack, alpha here. So obviously, if it's a higher angle of attack, we're redirecting more and more air, so you produce more and more lift, and it'll be proportional to your speed squared. You can see if you have a more efficient coefficient of lift, like you have a really thin, low profile airfoil, you can produce more lift. If you have a really dense medium, like you're going through water instead of air, more lift. If you have a larger angle of attack, more lift. If you're going faster, more lift, and so on. So, keeping that in mind, let's start off of, let's say you have your airfoil, and we're actually going to tilt it down, just like I drew before. And let's say you drop it in the air, and it's going to start, it just starts falling. What's going to happen is, oh boy. I'm going to see if they have any chalk. She's gone. Alright, we're just going to big do. So we'll start off with our airfoil like this. We're gonna say it's a magic airfoil so that it doesn't change its angle at all. We're gonna drop it through the air. It's gonna pick up speed, and then it starts producing some amount of lift, and that lift is because it's pointing this way, starts pushing it forward. And eventually you're gonna get to some equilibrium where all those forces balance out, and it's going to be moving down at some speed and forward at some speed. We call that our glide angle. And that caveat about it being magically oriented is very important because that's not what we have in our paragliders or any plane. And for a paraglider, we have sort of a special setup here. This is completely useless. All right, try to do it with my fingers. With our paraglider, we have our glider sitting above us, and we have our weights suspended below. And what keeps the glider in that orientation is we have this pendulum stability. If the glider were to get in front of us, the weight of our body gets pulled underneath because there's nothing to hold it in that position, so we'll swing back underneath. Similarly, if we swing it forward of the glider, it returns us. If you're looking head on at the glider and it rolls off to the side, it's the same idea. The pendulum stability holds us here. And for the yaw, because the wingtips are curled in, if it weather vanes off to the side, the side that's in front sees more force here, so that weather vanes it back into the wind. For an airplane, they don't have that same pendulum effect, but what they do have is, you're looking side on the plane, most of the weight is actually in the front of the plane, and then because the wings are inclined like this, the center of lift is in the back. So if it's flying too slow, it doesn't produce enough lift and it starts to drop. So it'll fall to the ground, pick up speed, and recover. Is that your race?
Yes.
Sweet, thank you so much. Where'd you find this?
I asked her.
Oh, sweet. Awesome. No, let's try to draw this again. Oh, that's so much better. All right. Here's our paraglider. Here's our center of lift, drag. Here's our weight. Same idea. All we've done is instead of the center of weight acting in the middle of the wing, it's way down here. So that's going to give it some pitch stability. And then, so I want to talk about, or what I was trying to talk about before is if you were to drop this guy in the air and it's not moving forward at all, as it starts to drop this, as it starts to fall through the air, it'll start to get pushed to the left here. It'll pick up some speed, and it will keep picking up speed until eventually this lift vector is strong enough to offset the weight and it doesn't pick up speed anymore. And referencing our angle here, you can see that you get different effects of if I had a glider that's really shallow to the horizon like this, it's going to have a very large angle of attack, this angle here, and referencing our formula before, because it has a large angle of attack, it produces a lot of lift, everything else being equal, which means in this situation, it doesn't have the velocity is relatively lower as compared to we had our airfoil oriented like this. Our relative weight is something like this. Our angle of attack is really small. So in order for the weight and lift to offset, it has to be going really, really fast. So we'll have our velocity being greater.
It's like the speed bar, right?
Exactly. So yeah, what the speed bar actually does is we have our glider here, and you have your A lines, and your B lines, and your C lines, and your brakes are connected over here. And if you look at the mechanics on the speed bar, they have a pulley system on the A risers. What they'll do is they'll shorten that line, so it tilts the whole glider down, and it changes this angle of attack. And a lot of times people are confused with angle of attack. They think of how the glider is relative to the horizon, where it is above us. And the glider can pitch. We can play some games. We can force it to pitch down, but that pendulum stability is always going to bring it back overhead unless we're doing something like holding a turn. So it's very important that you don't get confused with thinking of the pitch of the glider, sort of this motion is not related to our angle of attack. Angle of attack is always where is the wind coming relative to how the glider is sitting. So you can have a situation like, let's say you're in a really tight turn or a spiral dive. You could have something like this, the glider's pointed down, and you're over here, and you can have a very low angle, but you have a very high angle of attack even in this situation if the wind is coming in like this, diving at the ground, even though your pitch seems like it should be a low angle of attack. So those two concepts are easy to get conflated with each other, but they're not the same. Okay. So you can actually measure what happens with all the different angles of attack. Which is a plot here. This is going to be our vertical speed, and it's going to be our horizontal speed. And we're going to look at what happens when you fly with different geometries of the glider. So if you're doing absolutely nothing, you're going hands up, nothing on the speed bar, you're just letting the glider do its thing, we call that our trim speed, and it's going to be something like minus 200 feet per minute, and we'll call it 22 miles an hour. And just for reference, that's going to be us just letting the glider do what it wants to do.
I have a question for you. Is that trim speed the number that's affected by like the geometry of your glider, your weight, the weight of your harness? Is that the thing that people like try really hard to calculate, or is that set?
Yeah, so the trim speed is going to be, so when we talk about our lift is proportional to our coefficient of lift, density, angle of attack, velocity squared. So if you do your algebra on here, you get your velocity is equal to the square root of lift over yada yada yada.
So all of those things are just what determine your
yeah. So basically, assuming all else is equal, that you have the same airfoil, the same density, the same weight, all that's how you get a particular trim speed. The trim is defined as just letting the glider fly as it wants to fly without any deviation. Because the two things we can control are, we can add brakes, which actually what it does, it bends the trailing edge down and adds what we call camber. So whenever the air comes in, it's deflecting it down even more. And then of course we can change the angle of incidence by shortening the angle lines. So if you were to plot what that does at different settings, we'll start off from our trim speed, and we'll look at like min sync now. So somewhere around quarter brakes or so. And what that's going to do is it's going to slow the glider down, but it's also going to make the sink rate a little bit better. We'll say slight improvement in sink rate, slight reduction in speed, and that's going to look, the airfoil will be at the same angle here, and it'll have a little bit of brakes, so a little bit of camber. And if you slow it down even more, so you add a lot of brakes, what will happen is you'll slow down even more, maybe down to something like 15 miles an hour, but your sink rate actually gets worse, starts to do this. And at some point, if you slow it down way too much, you have a lot of camber, or you could do the same effect would be if you were flying really, really steep. So think about it. What would happen is your relative wind is starting in like this, and it's approaching more and more and more steep in this. You're flying with a huge angle of attack, and at about 12 miles an hour, what happens is if this angle of the wind comes in too steep, it can't stay attached to the top surface. It's going to come in, it's going to keep going, and it's going to wrap around. It's going to make these turbulent vortices. What we call this is a stall. A stall means that the air no longer follows our airfoil shape. It starts creating all this drag. So suddenly our drag starts going up a lot. So if we're looking at our airfoil here, remember we had our lift and our drag and our weight. Our drag starts growing tremendously at a very non-linear rate. So that's going to further reduce our speed, which means a further reduction in lift, which means we're going to fall even faster, which means that our angle is going to get even worse. More drag is this feedback loop, and then you're no longer flying, you're just falling out of the sky and you turn into a parachute. So that means your sink rate starts falling through the floor and your speed goes to basically zero. So that's the slow end of the curve. And then the opposite end is if we start flying faster and faster, is we'll go faster for a higher sink rate, then we go even faster, even worse sink rate, even faster. And you can plot this through, and if you link all this together, you get this shape that looks like this. And I guess over here our airfoil is pointing really far down. And every aircraft has a characteristic shape like this called the polar curve. For airplanes and gliders and stuff, their curve looks really nice. It's like this. It's very efficient. It's basically their proportional vertical and horizontal speed don't really change depending on how fast they're flying. Everything scales proportionally. So if they want to go twice as fast, they just sink twice as fast. That's really efficient here because if you were trying to glide the same angle, if you had a perfect polar curve, it would follow this angle just like this. And you can fly any speed you wanted, you would always get the same glide. But of course, no aircraft is perfect like that. And the more bent this curve is, sort of the less efficient the glider is. So ours looks something like this, maybe like a sailplane would look something like this, and actually like a competition glider, something really long and skinny is going to have a more favorable polar curve, and then a mini glider is going to look more like this. So the important points to know about this is not necessarily the exact numbers, but just sort of the effect on what your glide is going to do based on how fast or slow you're flying. So if you wanted to fly really, really fast, you're flying at top speed, your glide's terrible. If you fly really, really slow, your glide's terrible. And there's going to be some magic point where you get the absolute best glide, And on modern gliders, that's usually at trim or maybe just like a little bit of speed bar, and it's a little bit different for each glider. And fortunately, the exact point is not super important for you guys. You know, it's going to be on the order of trim. But the one that I think is a little more important learning off is people love to think of their brakes as their I don't want to come down button, which is not what they are. I'm going to redraw this curve just so things a little cleaner. Here's our polar curve, and here's our trim speed, here's our minimum sink. So your min sink, you're flying a little bit less sink rate, but we're talking something like, you know, if your trim is 200 feet per minute, your min sink is like 180. And if your trim is, you know, 22, then min sink's like 20, whatever the numbers are. So you want to think about your min sink here. It's not I'm going to stay up longer because I'm flying with brakes on. You know, if you're flying off a 600-foot hill and you change your sink rate by 20 feet per minute, you're going to add like 10 seconds of flight time. So the brakes do not keep you up in the air. What they do is they make you fly slower so that if you're in a place you like if you're in some lift, you can stay in that lift for longer, which allows you to work it and stay up. What are we on time?
It's 9:30.
Oh, perfect. We have tons of time. So, all this good stuff. Now let's talk about how this applies to flying. So we're going to look top down. Let's say you're soaring along a ridge. This is all the ground. And this is our glider. And let's say the wind is coming in like this. We'll say it's coming in at 15 miles an hour at 45 degrees to the ridge. And you're flying along at 22 miles an hour cruise along. So if you wanted to go back and forth along this ridge, in order to not leave the ridge line, you would have to be flying at a steeper angle than the wind, so that when you add these two arrows up, you get this guy here, and then this is your net speed difference. So if you wanted to stay the same distance from the ridge, you would be inclined into the wind a bit, and your toe motion would be along the ridge. And similarly, if you are going the opposite way, and you want to stay at the same difference, you're going to be inclined at the same angle here, but the opposite direction. So now your wind is like this, and your airspeed is like this, and your net speed is this guy. So if you're ridge soaring crosswind, when you go into the wind, you're going to be moving really, really slow, and we're going to be moving with the wind, you move really, really fast. And this is all relative to the ground. So as far as the glider is concerned, it's always the same amount of wind, no matter which way you're flying. So if you're just feeling the wind in your face, it feels the same whether you're flying into the wind or crosswind or downwind.